So in section 4.3, here we're actually solving higher order ODEs with constant coefficients. Our equations are going to look like this, where we have constants, a sub 1, a sub m minus 1, a sub n was the first one, and so forth. These will be homogeneous equations. They're going to be equal to 0. The leading coefficient, a sub n, cannot be equal to 0. These are nth order ODEs, and so they'll have n linearly independent solutions that we'll solve for. So by the end of the section, we're going to be able to recognize an nth order homogeneous linear ODE with constant coefficients. We're going to define and build the characteristic equation, and then determine the solution forms from the roots of that equation. We're going to look at distinct roots, repeated roots, complex roots, and then zero roots. We'll do those 4 examples, and we'll end with a short initial value problem where you solve for the constants of integration. So if you have a higher order linear ODE with constant coefficients, that's homogeneous, then the solutions can be written in the form of, I'm going to make that an x because I think I changed all the t's to x, e to the mx. We're going to look for solutions in the form of e to the mx. And then when we substitute that y into the equation, we're going to get all those exponentials. You're going to have all like terms. And the e to the mx is going to be, you can factor it out. And because when you factor it out, you can divide by it because e to the mx is never equal to 0. And you can get rid of the exponential, and that'll leave you with a polynomial equation. That looks like this. So basically, this m, that's going to be our variable, is going to be raised to the power that's equivalent to the derivative. So for a sub n, y to the nth derivative of y, that's going to give you still that same coefficient, a sub n, but you're going to get m to the nth power. So the nth derivative gives you the nth power. The m minus first derivative gives you the m minus first power, and so forth. It's going to give you a polynomial equation that hopefully you'll be able to solve. And if you have distinct real roots, so these are our 3 cases. Case 1, distinct real roots. We're going to have n solutions. So if m1 through mn are all distinct and real, then our solution is going to be, or our general solution is going to be c sub 1 e to the m1x plus c sub 2 e to the m2x plus, and so forth for each one of those m's. If we have multiplicities, so if you have repeated roots, if you have a root m with multiplicity k, then one solution is going to be e to the mx. The next one is going to be x e to the mx, and then x squared e to the mx. Notice that you're multiplying the previous solution by an additional x for each one of those k's up to a multiplicity of k. So that'll give you x to the k minus 1 e to the mx. as that highest power. So this is case 2, repeated roots. We'll just write that here, repeated roots. So we have distinct real roots, we have repeated roots, and then case 3, complex roots. Now we know that if we have a quadratic equation, we can have complex roots. So we could have something in the form of m equals alpha plus or minus beta I, where beta is not equal to 0. If beta is equal to 0, then you have a real root, m equals alpha. And our solutions are going to look like that e to the alpha x that comes from the real part of the complex number. And then from the imaginary part of the complex number, the beta I, we're going to get sines and cosines. We'll get cosine beta x and sine beta x. So our two solutions here are going to be e to the alpha x cosine beta x and e to the alpha x sine beta x. And you can put them together by multiplying by those constants C1 and C2 to get the general solution to the equation. So we'll look at complex roots as well. So let's do some. So first thing I'm going to do is make a substitution. I'm going to let y equals e to the mx. And then I think in this case, I'm going to substitute it in just to show you how the e to the mx will factor out. Then y prime is the derivative of e to the mx. You would carry down the m, and you get e to the mx. And our second derivative, y double prime, m is just a constant, so we don't need the product rule. Just the derivative of e to the mx will carry down one more m. We get m times m is m squared, e to the mx. So when I substitute these in to the equation, I'm going to get my second derivative is m squared e to the mx minus 3 times my first derivative, m e to the mx, plus 2 times y e to the mx equals 0. Notice that we have that e to the mx in common. You can factor it out. Factor, factor, factor. And we're left with m squared minus 3m plus 2 equals 0. And from here, you could divide by e to the mx. And 0 divided by anything other than 0 is 0. And that leaves us with m squared minus 3m plus 2 equals 0. This is called the characteristic equation. M squared minus 3m plus 2 equals 0. Notice how it relates to the original differential equation. We have our second derivative gives us the second power, m squared, minus 3 times the first derivative gives us minus 3 times m to the first, and then plus 2 times y, no derivative of y, gives you just plus 2. Is equal to 0. So after this one, we're going to go straight from the equation to our characteristic equation after we make this substitution. We're going to say let y equal e to the mx, and then we're going to say our characteristic equation is, and here we could solve by factoring. This factors into m minus 2 times m minus 1. And so we get m is equal to 2 and m is equal to 1. Gives you two distinct solutions. Each solution will give you one solution to the ODE. If m is 2, remember we're substituting in y equals e to the mx. We get y sub 1 is e to the 2x, and then y sub 2 is e to the 1x. And our general solution is y equals c1 times y1 plus c2 times y2. So y equals c1 e to the 2x plus c2 e to the x. When you have two distinct solutions for m, that's going to give you two linearly independent solutions to the equation. Let's look at repeated real solutions. That's what we'll get here. Notice that we have a third order ODE. That means that we're looking for three linearly independent solutions, y1, y2, y3. And we can put them together to get the general solution, c1, y1 plus c2, y2 plus c3, y3. So I'm going to let y equal e to the mx, and my characteristic equation then from my third derivative is going to give me m to the third minus my second derivative will give me m squared minus my first derivative minus m plus no derivative. That's just going to leave me with the coefficient plus 1 is equal to 0. This gives me this third order polynomial equation to solve. I believe that I can solve this by grouping. I'm going to group the first two terms, which have a common factor, GCF, of m squared. And my second two terms have a greatest common factor of -1. And now we have that m minus 1 in common, so we could factor out m minus 1. And that leaves us with m squared minus 1. And then m squared minus 1 is the difference of squares. It factors into m minus 1 times m plus 1. So here I can combine those two m minus 1 factors to get m minus 1 squared times m plus 1 equals 0. From here, I get two solutions. I get, from this first factor, I get m equals 1 multiplicity. Let me write that out because it's the first time. Multiplicity 2 because it shows up to a power of 2. So here we have repeated solutions, And then from the second factor, we get m equals -1, multiplicity 1. We don't really have to write that. So from the m equals 1, it's going to give me my first solution is e to the 1x, which is just e to the x. And then for the multiplicity 2, it's going to give me a second solution that takes that first solution and just multiplies it by x e to the x. If I had a multiplicity 3, then my y3 would be x squared e to the x, and so forth. You would just increase that power of x for each additional multiplicity. And then in this case, my y sub 3 comes from this m equals -1, and that's going to give me e to the -1x, which is just e to the -x. So here my general solution is y equals c1 times y1 plus c2 times y2 plus c3 times y3, or y equals c1 e to the x plus c2x e to the x plus c3 e to the -x. So when you have repeated solutions, you're going to have that same exponential. You just multiply by x for the second solution. If you have a higher multiplicity, just multiply by an additional x, and so forth. Let's look at complex solutions. So here I have a quadratic, or I will have a quadratic. I'm going to let y equal e to the mx, and then my characteristic equation is m squared, that corresponds to my second derivative, plus 4m corresponds to plus 4y prime, plus 13 corresponds to plus 13y is equal to 0. So m squared plus 4m plus 13 does not factor. Because I have m squared plus 4m, I'm going to go ahead and solve by completing the square. I'll bring that 13 to the right side, and then I'll complete the square by taking half of 4. You could do that off to the side if you want, and then squaring the result. Half of 4 is 2, 2 squared is 4, and so I'm going to add 4 to each side of the equation to get m squared plus 4m plus 4, which factors into m plus 2 squared, is equal to -9. -13 plus 4 gives you -9. Apply the square root property to get m plus 2 equals plus or minus the square root of -9. The negative under the radical gives you a complex number, gives you I, and the square root of 9 is 3. So this gives you m plus 2 equals plus or minus 3i. And then bring that 2 over to the right side to get -2 plus or minus 3i. You have complex solutions. When you have complex solutions, you end up with solutions that contain sine and cosine. The explanation for that is given in the textbook, and just with a brief lecture, I don't go into the explanation. I just do very brief. So here, our two solutions are going to look like this. You're going to have e to the negative 2x. That exponential comes from the real part of our solution for m. And then you have a sine and a cosine. So I'm going to start with sine. Then take the real part of the imaginary part of the complex solution, 3, sine of 3x. And then y2 is going to be e to the negative 2x cosine 3x. And the general solution is, I'm going to factor out the e to the negative 2x to get c1 sine 3x plus c2 cosine 3x. So if you have complex solutions for the characteristic equation, you're going to end up with sines and cosines. Let's look at zero roots. Here again, I'm going to start y is equal to e to the mx. My characteristic equation is from that fourth derivative, you get m to the fourth, plus from the second derivative term, you get m squared is equal to 0. You can solve this by factoring out m squared. And you get m squared equals 0, or m squared plus 1 equals 0. From m squared equals 0, you're going to get m equals 0, multiplicity 2. From m squared plus 1 equals 0, you're going to get m squared is equal to negative 1. And then applying the square root property, you get m equals plus or minus the square root of negative 1, or m equals plus or minus I. So we have m equals 0, multiplicity 2. That's 2 solutions. And then we have plus or minus I. That's 2 solutions, giving us 4 solutions to this fourth order ODE. Let's see what they look like. So from y sub 1 is going to be e to the 0x. E to the 0 power is just 1. So y sub 1 is equal to 1, just a constant. Now that's multiplicity 2, means that y sub 2 is going to be 1 times x. You just take the first solution, multiply it by x. So we just get x. Y sub 2 is x. From m equals plus or minus I, this is a complex solution. But the real part of that complex number is 0. So we're going to have that e to the 0x, which is going to be 1, meaning that e is going to drop out. And we're left with just plus or minus I. And so our third solution is going to be sine, the coefficient of I is 1, sine 1x, and then y sub 4 is cosine 1x. So we have 1, we have x, we have sine x, we have cosine x. Those are our 4 linearly independent solutions. And together they give us our general solution Oh, come on. C1 times Y1 plus C2 times Y2 plus C3 times Y3 plus C4 times Y4. Now, first term, you could just put C1. So there's our answer. And then the last example for this worksheet is solving an initial value problem. In this case, we're given the second order ODE, but we're given two initial values. Initial values or initial conditions. If you're given two initial values, you could solve a second order ODE to find the particular solution. Initial values are also called initial conditions. So I'm going to start by letting y equal e to the mx. And my characteristics equation then is m squared plus 9 equals 0. We can solve by bringing that 9 to the right side. We get m squared equals negative 9. Apply the square root property to get m equals plus or minus the square root of negative 9, which is plus or minus 3i. So because the real part is 0, our complex solutions are going to be just contain sine and cosine. So I have y sub 1 is sine 3x. Y sub 2 is cosine 3x. And my general solution is y equals c1 sine 3x plus c2 cosine 3x. By the way, the test on chapter 4 does contain one of each one of these types of questions on it. So you definitely should know how to solve each of these types. My initial conditions are y of 0 equals 2 and y prime of 0 equals negative 3. So using those, I can solve for C1 and C2, and it gives me what's called the particular solution. I am going to, because I need y prime, I'm going to go ahead and take the derivative here. The derivative of sine is cosine. Derivative of 3x is 3. So that's going to give me 3c1 cosine 3x. And then for my second term, the derivative of cosine is negative sine. Derivative of 3x is 3. So that's going to give me a minus 3c2 sine 3x. Okay, now y of 0 equals 2. I'm going to substitute 0 into this equation, and I get C1 sine of 3 times 0 plus C2 cosine 3 times 0. So I know that sine of 0 is 0 and cosine of 0 is 1. So cosine of 0 is 1, sine of 0 is 0. And that tells me that 2 equals, this whole first term just drops out. And on the second term, I get 1 times C2. So 2 is equal to C2. And then I know y prime of 0 is negative 3. So I'm going to substitute 0 into that y prime, and it gives me 3c1 cosine 3 times 0 minus 3c2, c2 is 2, sine 3 times 0. But again, sine of 0 is 0, so this drops out. Cosine of 0 is 1, so this part right here is 1. Oh. Let me zoom in on that. So this gives me -3 equals 3 times c1 times 1, or 3c1, divide by 3, and we get c1 equals -1. So c2 is 2, c1 is -1. I'm going to go back to my general solution, and this is going to give me the particular solution. Let me spell that properly. Particular solution where C1 is -1, so that'll give me negative sine 3x, and C2 is 2 plus 2, that's right here, C2, cosine 3x. This is the equation that passes through the point 0, 2, and at 0 has a derivative of -3. And that's all we have for 4.3. For the brief lecture for 4.3, we looked at an initial value problem. We did where we have 0 roots. We did where we have complex solutions. We did where we have repeated real solutions and distinct real solutions. Okay. And we'll come back later with section 4.4. Thanks for watching, and we'll see you on the next video. Bye-bye.